Okay, let's talk about vector spaces and linear systems. We will be talking about various vector spaces associated with a matrix. We know that a linear system can be represented by a matrix. And these vector spaces have a geometrical as well as algebraic significance. Okay? First of all, the row space of a matrix is the span of the set of its rows. Okay, so if you think of the rows of a matrix as vectors, and we can certainly take the span of those vectors, then that's what the row space is. It's the span of the set of vectors represented by these rows. The row rank is the dimension of this space, so we know what dimension is, which is the same as the number of linearly independent rows. Okay? We have this lemma. If two matrices A and B are related by a row operation, that is, if you exchange rows or you multiply a row by a scalar constant, or if you add a multiple of another row to a given row, then the row spaces of these two matrices are equal. In other words, the row space of A will be equal to the row space of B, whether you do row exchange or row multiplication or row linear combination. Therefore, row equivalent matrices have the same row space and therefore the same rank, or same row rank. Recall that row equivalent matrix means that you can arrive at one from the other by a sequence of row operations. All right, now, why does this proof make sense? Well, notice that every one of these operations is kind of a linear combination. Here you're just exchanging rows. Of course, you're not going to change the span of the rows if you just exchange two. Here you're just taking a linear multiple, a scalar multiple. That's basically not changing the vector, it's only scaling it up. And here you're taking a linear combination. And recall that these row operations are reversible. So you're only taking linear combinations of rows of A to get rows of B, and you can do the same thing and vice versa. So it makes sense that the span of these, is the same as the span of these because these are just linear combinations of these, and vice versa. All right, so let's see what the proof says. Okay. If we take this corollary, it shows that when A goes to B, then each row of B is a linear combination of the rows of A. Now let's take a look at that corollary. It should be right here. Corollary 132.4. So let's go back. Okay, so here we have it here. When one matrix reduces to another, each row of the second is a linear combination of the rows of the first. Okay, so we're just getting from one matrix to another via a process of linear combination. And that's also pretty evident from the form of these operations. Okay, in other words, each row of B is an element of the row space of A because they're all linear combinations of those rows. Right? It follows that the row space of B is contained in the row space of A because any member of the set row space of B is a linear combination of the rows of B, so it's a combination of combinations of rows of A. So the linear combination lemma tells us that such a combination of the rows of B is also a combination of the rows of A. So it's in the row space of A. On the other hand, recall this lemma, which says that row operations are reversible. I won't turn there because I just mentioned this. So if A goes to B, then B goes to A. So we can also have that the row space of A is contained in the row space of B by the very same argument. Okay? So the upshot is, if you get one matrix from another through a series of row operations, it will have the same row space as the original matrix. Okay. Another important lemma that we'll be using is that the non-zero rows of an echelon matrix make up a linearly independent set. Okay? And this kind of makes sense. If you have an echelon form matrix, you have this stair-step structure. And if you imagine, and you may have 0 rows here, and you imagine if you have a linear combination of such vectors, then the coefficient of the first vector must be 0 because no other vectors have a non-zero component there. And if this one has a 0 component, then this one will also have a 0 coefficient, and so on down the line. All right, so that's kind of the intuition behind this lemma. I think in the actual proof we'll use things that we've proven already. All right, so here we have lemma 132.5 says no non-zero row of an echelon form matrix is a linear combination of the other rows. Okay, you can go back and take a look at that. I think it's right after here. Okay, and it's right here. No non-zero row in an echelon form matrix is a linear combination of the other non-zero rows, which is what we need. Okay, and as I mentioned, the proof of that is pretty much the reasons that I mentioned in talking about this diagram here. All right, now that takes care of this lemma. Okay, remember that if a row is a linear combination of the other rows, that means that the rows are linearly related. If there's no non-trivial linear relation, then we have that the rows are linearly independent. Okay. Okay, so let's do an example. So we have a matrix before Gauss's method and the matrix after Gauss's method have equal row spaces by the two things that we've just shown. Here's my matrix before Gauss's method, and then apparently these row reductions will take me here. Notice there is a 0 row here. So in fact, the row rank is 2. Okay, because I can reduce this to 2 linearly independent rows. So Gauss's method actually produces a basis for the row space, because it is a linearly independent set that spans the row space. We also have the notion of column space. The column space of a matrix is the span of its columns. The column rank is the dimension of the column space, the number of linearly independent columns. So this is the very same concept. You have columns, which you can consider vectors. You can take linear combinations of these columns. And we're going to look at bases of this column space and so on. We can do the very same thing with columns that we just did with rows. Okay. Let's see if I did this right. Whoops. Went ahead somehow. Okay, here we go. Okay, all right. Now, here's an example. If I have a linear system of linear equations, I can write this in this vector form. We know we can write this in the matrix form, right? We can write it as 2, 3, minus 1, 1/2 times xy is equal to d1, d2. That's one way we can write this. But we can also write this in vector form. Right, look at these two equations. Here we have x multiplying 2 in the first equation and minus 1 in the second equation. Here we have y multiplying 3 in the first equation and 1/2 in the second equation. So we can combine these two equations into one single vector equation. Now notice that what we have here is the vector of constants is expressed as a linear combination of the columns. So if this vector of constants is in the span of the columns, then we have a solution. In other words, if this vector of constants is in the column space, then we can have a solution. Now this shows why the column space is so very important. Okay? Right? And these columns are just the columns of this matrix here. All right, now, we've talked about row space and column space. We can relate the two concepts using the notion of transpose. The transpose of a matrix is the result of interchanging its rows and columns, so that column J of matrix A is row J of matrix A transpose. This AT is called A transpose, and vice versa. Okay, let's look at some examples. Okay, so if I want to find a basis for the column space of this matrix, now remember that's important because that will give me the set of vectors for which I can find a solution to the inhomogeneous equation. So if I want to find a basis for this column space, now I know how to find the basis of a row space, so I'm going to turn the columns of this into rows of another matrix. I do that by taking the transpose. So in other words, the first column here, 2 minus 1, becomes the first row of its transpose, 2 minus 1. The second column of the matrix A, 3 1/2, becomes the second row of the matrix transpose, A transpose. Now, if I reduce the transposed matrix, I'll get a set of vectors which I know has the same span as the set of rows here. Okay, so 2 minus 1 and 0, 2 have the same span as 2 minus 1, 3 1/2. Okay, but these rows here are exactly the columns of my original matrix. So if I change these rows into columns, I'll get a matrix for which the column space has the same span as the original matrix A. So it has the same column space as A. Okay. Okay. This basis, it shows the column space, is the entire vector space R2. Okay, because in fact, this is a basis with two vectors, and we know that the basis with two vectors must span a two-dimensional space, so it must in fact be the entire vector space R2. Okay, we continue in our investigation of column space by proving this lemma that row operations do not change the column rank. Okay, so we know that row operations don't change the row rank, that is the rank of the row space. It turns out that the same thing is true for the column space. Okay, in other words, if A reduces to B, then the column rank of B equals the column rank of A. All right, so let's read this justification. The proof will be finished if we show that row operations don't affect linear relationships among columns, because the column rank is the size of the largest set of unrelated columns. That is, the largest set of columns for which there is no homogeneous relationship is equal to the column rank. That is, we will show that a relationship exists among columns if and only if that same relationship exists after the row operation. Okay, this is exactly the first theorem of the book. Theorem, in a relationship among columns, row operations leave unchanged the set of solutions. Okay, so let's go back there and see what we're talking about here. I'm going to pause for a moment while I find this. Okay, here's the theorem that we're talking about. It's just the statement of Gauss's method that row operations give a system that have the same set of solutions. So how does that relate to this statement here? Well, we're just writing this homogeneous system of linear equations in vector form, right? This is the same as a system of m linear equations, linear homogeneous equations. So we can think of this as a linear dependence relation among these columns. Okay? And if I do row operations on the matrix corresponding to these column vectors, according to that theorem that we just looked at, that's not going to change the solutions for CI. Okay? So if I have a row relation among the columns of the original matrix, I'll have the same relation among the columns of the row-reduced matrix. Okay? It's a little bit confusing. Think about that. But basically the idea is that row reduction doesn't change this relationship because this relationship represents the solution of a homogeneous equation, homogeneous system of equations, rather. Okay, so we'll use this to show that for any matrix, the row rank and the column rank are equal. Okay. Let's bring the matrix to reduced echelon form. So just recalling reduced echelon form means you have a matrix. You have ones here in certain places. And everywhere you have a 1, you have a 0 everywhere else. Okay. And it's possible that you may have certain rows that are all zeros. Right? So these rows here are all zeros. And of course, it's also possible that you have certain rows that have not 0 or 1 entries, which is okay as long as this first entry is not, I did that a little bit wrong, this first entry is not a leading 1. Okay? So for instance, if I have a 1 here, and there's no leading entry in this column, it's possible that all of these entries are non-zero. Same here. For instance, if there's a column here, such that this 1 is the leading entry of the row, it's possible that I could have all non-zero entries here. So that's what your row reduced, your reduced echelon form looks like. Okay. Now, we know the row rank is equal to the number of leading entries, because that's the number of non-zero rows. We know that the rows that are non-zero in a reduced echelon form form a basis for the row space. So non-zero of reduced echelon form form a basis of the row space. Okay. All right. Now also the number of leading entries is equal to the column rank, because the set of columns containing leading entries consists of some of the EIs from a standard basis. And that set's linearly independent and spans the set of columns. All right, so what are we saying here? Look at this particular example. Here I just have 4 linearly independent rows with 4 leading entries. Take a look at these columns that correspond to the leading entries. These are the standard basis. Actually, I have 5 here. Okay. Standard basis is just I have 1 and 1 entry and zeros everywhere else. Okay. These are certainly linearly independent because, for example, if I have a linear combination of these vectors in the standard basis, Well, the coefficient of this first one must be 0 because all the others have entry 0 there. And you go on down the line, and that shows that there is no linear relation among the sets, among the vectors in this standard basis. On the other hand, any other column vector is going to be a linear combination of these standard basis vectors. Because, for instance, if I have a vector here that has entries 1, 2, 3, 4, well, that's going to be 1 times the first column, plus 2 times the second column here, plus 3 times the third column, and so on. So in the reduced echelon form matrix, the row rank is equal to the column rank because each is equal to the number of leading entries. All right, so there you have it. The reduced echelon form of the matrix shows in a simple way columns that span the column space and also rows that span the row space. Now, Lemma 3.3 and Lemma 3.10 show that the row rank and the column rank are not changed by using row operations to get reduced echelon form. In other words, the row rank and column rank of the reduced echelon matrix is equal to the row rank and the column rank of the original matrix. Since the ranks are equal for the reduced echelon matrix, the ranks for the original matrix are also equal. And that gives us our result. So we can define the rank of a matrix as its row rank or its column rank, because they're both equal. For example, let's consider the column rank of this matrix. It turns out that it's 3. Why is it 3? Because if you row reduce the matrix, now this is just echelon form, it's not reduced echelon form, but from this we can see that the row rank is 3, and it follows from that previous result that the column rank must also be 3. Okay, let's go a step further with what we've just shown. For linear systems with n unknowns and with matrix of coefficients A, but that's not necessarily a square matrix, but just any matrix of coefficients, the following statements are equivalent. The rank of A is R, and the vector space of solutions of the associated homogeneous system has dimension n minus R. So these two statements are equivalent. So what are we talking about here? Well, let's think of what this means in terms of a reduced echelon form. If the rank of A is R, then I'm going to have R leading entries. And the rest are zeros, you know about that. Okay, so there are leading entries. Right. Now, if I have n unknowns, that means n columns. Right. If I have n columns and R leading entries, I have n minus R non-leading columns. And these all correspond to free variables. Okay, n minus R free variables. But we know that each free variable leads to an additional dimension in the solution space. We write the solution to the homogeneous system as a linear combination of vectors, and each free variable corresponds to one vector. All right, so you can see that this shows a case where the rank of A is R and the vector space has dimension, the vector space of solutions has, to the homogeneous system has dimension n minus R. Those two concepts are related. So let's go through the formal statement of the proof. The rank of A is R if and only if the Gaussian reduction ends with R non-zero rows. That's true if and only if the echelon form matrices a row equivalent to A have R many leading variables. That in turn holds if and only if there are n minus R free variables. Okay, so we've explained how that means n minus R free variables means the associated homogeneous system has dimension n minus R. Okay, so again, keep in mind the picture of the reduced echelon form, and that clarifies why these two are equivalent. Now, let's consider the special case where the matrix is a square matrix. Okay, if the matrix is n by n, the following statements are equivalent. The rank of A is n, A is non-singular, the rows form a linearly independent set, the columns form a linearly independent set, and any linear system whose matrix of coefficients is A has one and only one solution. Now, let's think of what all these means. All of these are equivalent to the reduced echelon form of A is equal to the identity matrix. Okay. Clearly, if the rank of A is the rank of the reduced echelon form, then the reduced echelon form of A must be the identity matrix because you need to have a leading entry in every row and every column. We know that that's the same thing as saying that A is non-singular. We know that's the same thing as saying that the rows are linearly independent because here we have a basis of the row space which consists of all the rows of the matrix. We also know that row space and column space have the same dimension. So if the rows are linearly independent and the number of rows equals the number of columns, then the columns must also be linearly independent. Finally, we know that this means the same thing as saying that the matrix of coefficients has one and only one solution. Okay. All right. So we've talked through these equivalences. 1 is the same as 2, is the same as 3, is the same as 4. The last statement holds because a set of n column vectors is linearly independent if and only it's a basis for Rn. But the system that is the linear combination of columns equal to an arbitrary vector has a unique solution if and only if the vectors on the left-hand side of this equation form a basis. In other words, the columns of the matrix must form a basis for the n-dimensional space. Now, if the columns form a basis, then the columns form a linearly independent set, so we get the equivalence of 4 and 5. And there we have it.